Hello guys, welcome to another video. Today we're going to solve October 2024, Unit 3 of International Edexcel A-Level Physics. And let's start right away. So, let's look at question 1. A student used a steel sphere in an experiment to determine the viscosity of a liquid. The student used vernier calipers to determine the diameter d of the steel sphere. The student recorded a single measurement of D as 12.7 millimeters. Determine the percentage uncertainty in this measurement. Okay, so we have to find the percentage uncertainty. As discussed in earlier videos, we know there are several formulas of percentage uncertainty depending on the situation. Like basically, there's just one formula, but it kind of like the solution varies depending on the situation presented in the question. So over here, now we're just given a single measurement of D. No other information is presented to us. In any such case, no matter whether that's a vernier calipers, whether it's a meter rule, an ammeter, whatever device it is, what you're going to do, you're first going to find the resolution. Okay. The resolution is the smallest measurement that a device can make that you can find out from the reading that it measures. So this vernier calipers measured 12.7 millimeters. If you count the decimal places, there's just one decimal place. So it's basically like the smallest value would be 0.1 millimeters. That is the resolution of the vernier calipers. Now, we are not going to use the resolution in our formula. Instead, we'll be using half of the resolution. Why? Because our device, like the vernier calipers, for any reading that it can measure, like if it's measuring 0.1 millimeters, it can be just half of 0.1 ahead or behind 0.1 by 1/2. So we will use half the resolution for that matter. So that would be 0.01, 0.05 millimeters. If you still did not understand it, you can think of a meter rule. So we know that a meter rule can measure the smallest reading as 1 centimeter. But if something is just 1 centimeter, still it could be that when you're measuring, uh, it could be between 1 and 2 centimeters. So it could be 1.5, or it could be behind 1. So it could also be 0.5 centimeters. So that's why we divide the resolution by 1/2. So now we need to find the percentage uncertainty. Now we know the formula of percentage uncertainty is absolute uncertainty over the mean value times 100%. Now the mean value is just the reading that you took, the reading that you measure. So over here it's 12.7. So that's simple. We just write 12.7 in its place. The absolute uncertainty is over here the half resolution. In some questions, there could be a different way of finding the absolute uncertainty. It depends on what the situation is. So we write 0.05 over here and multiply it by 100. So we get 0.39%. So that's the resolution. And if we just write it to one significant figure, because the absolute uncertainty is 0.05, that would be 0.4%. There you go. I hope that's clear. Let's move on to part 2. The student repeated the measurements of D at different orientations and calculated the mean. Explain another technique she should use to determine an accurate value for D. The keyword in this question is accurate value for D. So we have to come up with an answer that will enhance the accuracy of the measured diameter. Since the student already took the mean, repeat readings, the mean, she also measured it at different orientations, so that's not an option. Now, then what can we do? Now, the accurate value measurement is based on what device you're using. So if you were using a meter rule, for example, in this question, then the answer would be according to the meter rule. If you were using let's say, a screw gauge, the answer would be according to that. Over here, we're using a vernier calipers. So both for the vernier calipers and the screw gauge, you can always talk about the zero error. Zero error is a systematic error, and it can affect the accuracy of the measured value. So, whenever you operate a vernier calipers or a screw gauge, the first thing you should always do before taking your measurement, before even placing the sphere in the jaws of the vernier calipers, you should find out the zero error. And how do you find that out? You basically close the jaws of the vernier calipers, okay, completely close it, and then you see that whether the zero of the main scale coincides with the zero of the vernier scale. Like if they perfectly coincide, okay, then there is no zero error. But if one of the zeros is ahead or behind, then there is a zero error. So first you find out what the zero error is, note it down, then you take your measurement, like you place the sphere in the vernier calipers, find out its diameter, and then the final value that you got, let's say your final value was 12.7, then you remove the zero error from that. Like you either add it to that value or subtract it, depending on whether it was a positive or negative zero error. So now of course we don't need to go into all that detail over here. It's just a 2-mark question, and we just have to say what technique we have to use to determine an accurate value for D. So the student should check zero error before taking or before measuring the diameter, and remove it, or rather than remove, because remove could also just mean subtract, while zero error could be corrected by either addition or subtraction depending on the particular situation. So, and correct it in the final reading. There you go. So we just check the zero error and we correct it. Remember, there are 2 parts over here, checking the zero error and correcting it in the final reading. You can't just say check the zero error. You have to mention both of these points. Part 3, describe how the student should determine a value for the density of steel. Okay, so this one is an easy question. Like, if you just think about density, density is mass over volume. And what's the connection of this information to the question that's given? In the question, we're measuring the diameter of a steel sphere. So now we have the mass and the volume. Those two things we need to find. We don't have them. We need to find them to find out the density. So from the diameter, we can find the radius. Okay. So uh, find the radius by dividing the diameter by 2. Now, why do we need to find the radius? Because we need the volume of the sphere. And the volume of a sphere 4 by 3 pi is 4 by 3 pi r cubed. So r is the radius. So we need to find the radius, then calculate the volume, the sphere, by using volume is equal to 4 by 3 pi r cubed. And then we have the mass. How do we find the mass? There's no information given related to it. So the student can just measure the mass of the steel sphere by using a balance. To find the mass of the sphere, the student should use a balance and then plug the values, like plug mass and volume, and density is equal to mass over volume. And there you go. Now, see guys, I could just have written all this information randomly, okay? But I structured it in proper sentences. Now, even if you put this randomly here, if you put all the points, you still get all 3 marks. But then why did I feel the need to like write it in a structured way? Because this brings practice to your work, especially for 6 marker questions. Many students hate those questions. They they hate bringing structure and coherence to their answers. But when you structure your answers, it shows your ability to present your work in a clear and organized manner. And it's easier for the examiner to follow. And it also helps you practice for 6 marker questions. So anytime you attempt a question, do it in a coherent and organized way. It will help you. All right, moving on to part B. Part B says the student placed the steel sphere in a transparent tube filled with the liquid. She arranged the transparent tube as shown. The student used a stopwatch to measure the time for the steel sphere to travel between the rubber bands. Describe how she should ensure that the steel sphere is traveling at terminal velocity between the rubber bands. You should include any additional apparatus required. All right, guys, so this question is about terminal velocity. So, terminal velocity, first, what is terminal velocity? It is a constant velocity that is achieved when drag force is equal to weight. Okay. Over here, since the tube is inclined, it would be the drag when the drag force is equal to a component of weight. But anyways, we don't have to mention the definition here. This is just to explain what terminal velocity is. The key word over here is that it's a constant velocity. It's a constant velocity. So we actually need to prove, or the student needs to prove, that between the two rubber bands, the velocity of the sphere, of the steel sphere, was constant. So for example, if at this point it was moving at 1.5 meters per second, then it was also moving at this point with 1.5 meters per second. This is what we need to prove. So how do we do that? Now, when we think of terminal velocity, there is just one formula related to it, which is the drag force, 6 pi times viscosity times radius times the terminal velocity. This V is the terminal velocity. But this formula doesn't make sense here because we don't know any of the other things, and the question even doesn't mention them. So we don't need to use this formula. Then what do we need to use? So since it's velocity, uh, all velocities, no matter what they are, use the formula distance over time. Now we don't just have to say how the student will find this velocity. We have to say that whether the steel sphere was traveling at terminal velocity between the two rubber bands, between point A and point B, was it traveling at terminal velocity or not? How do we prove that? We can prove that if we show that the velocity was constant. How do we show the velocity is constant? So let's just choose some random points. Uh, let's say that we have this point C here and this point D here, and then we have some point E and F here. Okay. So if we prove that the velocity between point C and D is the same as the velocity between point E and F, then we can prove the sphere was traveling at terminal velocity. Okay, you could even use more points. It's not just limited to like two sets of points. You could also take 3 or 4 sets of points. Um, so for the first 2 set of points, we could measure the distance using a meter rule. We can measure the time taken between the 2 points using a video camera. We can record, we can watch the video in slow motion to exactly see when it passes, what's the time when it passes through C, and what's the time when it passes through D, and subtract the times to get the time taken. Similarly, we can do the same process between points E and F. We can measure the distance between E and F. We can also measure the time using the same technique. Use a video camera to record the motion, watch the video in slow motion to find out the exact time, subtract the times to get the time taken. Then we find the values of both the velocities using distance over time and see if we get the same value. Of course, we don't have to deal with values here. We're not provided with any values. But if the values are the same, this means the sphere acquired terminal velocity here. So now we're just going to write that information. So at first, so the student can choose two sets of points between the rubber bands. We can also, like in any of your questions where there are diagrams, and you can also use the diagram to your advantage. Like you can draw something there and then mention that in the answer if you think it will elaborate your answer. Not it's not necessary, but if you think it will elaborate your answer. So between the rubber bands, measure the distances measure the distance between the first set of points, and then we can mention C and D on the diagram. And between E and F. Okay, so now we have two distances. Distance 1, distance 2. Then now to find out the time, taken, the student can record the motion of the ball using a video camera and watch the video to track. Watch the video in slow motion. That's important. You have to say that the student must watch the video in slow motion to track when the ball passes between C and the ball passes point C and D. Um, subtract the time, subtract the 2 times, you get the time taken. Repeat the same process for points E and F. So then the student should use the formula. Using the formula terminal velocity is equal to distance over time. So I can say using the formula for either distance time values. She should compare if the velocity is the same. Between C and D and D and F. Sorry, and E and F. If it's the same, then it's terminal velocity. If it's the same, then it's terminal velocity. So, the main goal is to prove that if it will be the same or not. So you have to link back to how the student uses the measurements to prove, to find out whether it's the terminal velocity or not between the rubber bands. Now, you might be thinking that answer is pretty long, all the space is taken. Should we write such a long answer? It's not necessary. This is just one way to write this answer. I just used my own way where I just chose point C and D and points E and F. I I also think the answer got a bit long somewhere. You could even without choosing some points C and D, E and F, you can also generally mention some points. And as long as uh the concept is the same, which is measuring distances between two or three different sets of points, measuring the time taken, and then finding out the terminal velocity using the formula distance over time, and then comparing. Uh, so if the values are the same, it's terminal velocity, otherwise not. Then as long as it's the same concept, you'll get the marks. Also, uh, I will remove the word terminal velocity over here because this formula is not for terminal velocity, it's just for velocity. If the values are the same, then we can conclude it's terminal velocity, otherwise not. So that was question one of unit three, sorry. I think there is a part left. Okay, let's continue with part C. Part C is the student determined the viscosity of the liquid as 0.72 pascals second with a percentage uncertainty of 6%. The viscosity of castor oil is 0.65 pascals second. Deduce whether the liquid could be castor oil. Again, a very common type of question that appears in Unit 3. You have to say whether the liquid is castor oil or not. How do you do that? So, in any such question, so what did they tell you? They told you the viscosity of the liquid and its percentage uncertainty. So first, we are going to find the range of viscosity of the liquid. Okay, so in what range is the viscosity? So let's find 6% of 0.72 first. So that's basically 6% is 6 over 100. 6% of 0.72 is 6 over 100 times 0.72. Let's calculate that. That gives us 0.0432. So this means the viscosity of liquid would be in the range of 0.0432, sorry, 0.72 minus 0.4043 to 0.72 plus 0.043. Okay, the viscosity is in the range of this. So that's basically so 0.72 minus 0.043 is 0.677 and 0.72 plus 0.043 is 0.763. So this is a range of viscosity of the liquid. Now the viscosity of castor oil is 0.65. It's below this range. So the liquid is not castor oil. So since the lower limit of viscosity of the liquid is greater than the viscosity of castor oil, the liquid is not castor oil. So by finding the upper and lower range of the viscosity, and then like checking if the viscosity of castor oil falls in that range, we can conclude the answer. So that's like the end of first question of unit 2. Unit 3, we will continue with the second question in the next video. Uh, you guys can comment if you have any questions or if you have any suggestions to solve a certain paper. Um, all the best for your exams in the January series. Bye bye.